Herbots, Mark MANGUS, NERIC, AJ WOOLSON, Dr. CULBERTSON, Barry WILKENS, Austin Casey, Alex BRIMHALL, Clarissa Watson, Saloni SINHA, and ACHARYA, done with Arizona State University and SIO2 NanoTech, as well as the ion beam analysis of the material facility at ASU. I'm going to be presenting for Austin Casey because he couldn't be here today. So, why do we need to detect light elements in sensors? The answer is percolation. And which light elements do we need to detect and that do percolate and damage the sensors? There's carbon, oxygen, sodium, and silicon oxide. So basically, the ion beam analysis detects the monolayers of carbon, oxygen, and sodium in sodium dioxide on Si100 and titanium nitride in Si100. So what we do here is we combine RBS, Rutherford Backscattering Spectrometry, with ion channeling and nuclear resonance to increase, so basically ion channeling decreases the substrate yield by a factor of 30 to 40, and the nuclear resonance will increase the signal. For oxygen, increases by a factor of 23. For carbon, it increases by a factor of 128. And then in this talk, we'll look at how much the detection of sodium actually increases. So why do we need to detect these light elements, carbon, oxygen, and sodium? Basically, these sensors can degrade due to these contaminants, and especially from the charged mobile ions of sodium. What we need is we need readings to be stable for more than just a duration of some days. That's a problem that we're running into, and I'll talk more about a little bit later. And what we want is we don't want any percolation of fluids during the deployment of these sensors. This is called hermeticity. So the goal here is to detect the percolation of carbon, oxygen, and sodium from bodily fluids, saline, blood, and seawater into silicon dioxide on Si100 and titanium nitride on Si100. So what are the applications for hermeticity? We can look at them in context of single device medical implants, things such as artificial pancreas, blood pressure regulation, and moreover, we want to look at things like making a permanent glucose sensor, something that we need to last. Right now, you know, they're only lasting about 7 days. We need them to last longer than that. And then other applications include marine and air sensors, and then extended lifetime of solar panel encapsulation. So what is ion beam analysis, or RBS? RBS is the analysis of mass and depth profile based on the backscattering of an ion beam, a high energy ion beam. So if we can see here, this is a typical, you know, what an RBS spectra would look like. So gold is considered, you know, a more heavy element. On the x-axis, we can see the energy. The backscattering ion energy can corresponds to the target atom mass, whereas the y-axis, gives the count of the ions backscattered at any given energy. So right now, RBS can detect up to 5 monolayers of oxygen in Si100. What we're looking at here is the channeling can increase the detection by up to 30 to 50. So on this graph over here, you can see for rotating random, we're getting a lot of noise. And then for channeling, we're getting much less noise. And then you can see the oxygen signal here increased detection by a factor of 23, and you can see it corresponding in both rotating random and channeling. So what we did here is, like I said, RBS can detect up to 5 monolayers of oxygen, but we can take it down to about 1% of a monolayer. So here we're looking at the damage curve. Here again we can see the damage curve of the rotating random, and the channeling. There is no real trend in random. You can see the error bars are very high. Whereas in channeling, you have much more of a trend, and the error bars are much, much lower. So the samples we looked at are the dry thin films of the saline solution blood containing the light elements of carbon, nitrogen, oxygen, and sodium. Okay, so we're looking at the nuclear resonance detection of carbon, oxygen, and saline, and on silicon dioxide on Si100 and canine blood. So this is what we're going to be looking at first. So as we can see with the RBS detection, this is the initial, and then what we did with the ion beam analysis, you can see an increase at 3.07 MeV, increased detection again by a factor of 23. And then we're looking at the detection of canine blood on titanium nitride on Si100 again, the RBS of carbon at 2 MeV, and then you see at 4.31 MeV the resonance increased by a factor of 1. Okay, so next we're looking at sodium. What we did initially is, what we've done so far is we've characterized the amount of sodium in something that we know, something like baking soda. So you can see right here we have the sodium, and then now we're looking at the sodium characterized by our analysis. So you can see on the bottom here, at the lowest, this is just the RBS detection, so it's just what you see with RBS. Next, at the next highest energy, you can see that it's the resonance comes in, and then it is right at the surface. And then for the last one, you can see that it's going into one of the layers. Okay, so in conclusion, you can see that there is increased detection of light elements by ion beam analysis. The combining of the two can increase the detection by a factor of 32 to almost 3,200. And as we looked at, carbon increases by a factor of 3,840, and you can detect 0.1% of a monolayer. And then oxygen can go up by a factor of 300, and you can detect 1% of the monolayer. So what we did here is we looked at sodium. So here are the findings for sodium. We found that we can enhance detection by almost 46%. So those are the findings of the studies thus far.
It's time for questions.
At 1% of the monomer, that'd be like 12 atoms per centimeter squared. You can actually detect that with the RBS. And maybe at 0.1% would be 11.
Yeah, if you get the factor 100 with the resonance, and then with the factor 50 with the channeling, that gives you a factor 5,000 there. So you go from 5 milliliter to 1,000 milliliter. We have several papers about it.
Okay.
Very few people use it, even though it's usually not characterized. It's much more effective than the other.
So if you had an oxygen spike and an FE layer that was on the order of a 10th monolayer, you'd be able to detect that with this
Yes,
technique?
combining the resonance and the channeling. Just most people just do straight RBS with it random, and like she showed, you have all these noise. You can't see that little oxygen peak.
So what does it take to do the channeling? Is it just the sample alignment, detector alignment?
So for channeling, I think we got something especially ordered. Dr. CAUSEY ordered sample, so I think it takes a special type of substrate as well as the alignment.
Yeah, we use a goniometer and we align in front of the beam. But we got special sample. The samples she mentions were samples used in medical sensors because that's her major. And so I got them from a company. So we had substrate with very thin film of titanium nitride, so it was easy to channel.
Well, let's thank our speakers.